So fundamental theorem of algebra says whatever your degree of your polynomial is, in this case it says an nth degree polynomial, there are exactly that same number of zeros. So if my degree is 5, I should have 5 zeros. If my degree is 10, I would have 10 zeros. The zeros can be real, and now that we know about imaginary numbers, they can also be imaginary. So your first test in chapter 2, we only found real zeros. Now, because we know the imaginary number exists, we can find real and imaginary zeros. So we're going to find both. But we're still going to use the same process. So long division, synthetic division, like we're still going to be using that in the this next section here. So the problem says, how do we find zeros? We can graph it and find the real zeros. We can use the rational zero test, which you have to use if you're graphing it with the calculator, because that's kind of the algebra behind why you're looking up the numbers in the calculator. We'll use synthetic division, and we will also factor. And we factor it so that we can find the remaining zeros after we use synthetic division. So we are going to try and use that process to see if we can find all the zeros of the polynomial. However, the first 3 problems on here don't necessarily need us to look in the calculator or use synthetic division, because they might just be factorable. Or I could just solve them as they're written. So not every problem will we need to use synthetic division, but we need to use the calculator. So if you look at the first one for A, if I'm finding the zeros of x squared minus 2, I know that I would set this equal to 0, because that's what it means to find a 0. My y value is 0. And then, Brenton, how would you solve for x squared?
To the other side, and then you solve it.
Yeah. So we're supposed to find the zeros, we're supposed to find x. So he said take the square root. And Brenton, my solutions for x are?
I think it's plus or minus square root of 2.
Perfect, plus or minus square root of 2. Don't type it in your calculator and get a decimal. It's 1.41. We're keeping it exact. Don't forget the plus or minus. The power is 2. I should have 2 answers or 2 zeros. The second one we actually did on Tuesday as a little warm-up. So f of x equals x squared plus 1, which we made that 0. So negative 1 equals x squared. And using the same method that Brenton used for A, we would take the square root. Colin, what is the square root of negative 1?
Is it plus or minus 1i?
It is plus or minus 1i. Or you could just have plus or minus I if you wanted to. But the negative comes out and makes it I. And then we're taking the square root of 1. And again, my power is 2, so I should have 2 answers. In this case, they're both imaginary. But I still have 2 solutions for x. So they could be real or imaginary. The last one of these factoring problems, or finding the zeros, says x to the 4th minus 4. This one does need factored first, so I can't just take a 4th root. We have to be able to break it down a little bit. Does anybody know how you would factor x to the 4th minus 4? Emma?
X squared plus 2 times x squared plus 2.
Yeah, x squared plus 2, and x squared minus 2. So 4 is a perfect square. X to the 4th is a perfect square, and we would break that down as the x squared. These are conjugates. I have the plus and the minus, the sum and the difference of each. So once you factor it down this far, there isn't any other factoring that we need to do, but we can just then solve each of those quantities. So once you have it broken down to x squared, you don't necessarily need to factor further. You can just solve for x squared. So the first one I took the negative 2, and the second one I have the positive 2 on the other side. So again, taking the square root, what is the square root of negative 2? Emma, do you know what the square root of negative 2 is?
I squared of 2.
Yeah, and what goes in front of the I? Plus or minus, because I should have 2 answers there. So the negative comes out. The square root is a plus or a minus, so the negative makes the I. So now I have plus or minus I and the square root of 2. And then my other one, we solved as A. Again, don't forget the plus or minus. Power of 4, 4 answers. So 2 that are imaginary, 2 that are real. And that's how a lot of our answers are going to look, where you're going to have like some of each. So some will be imaginary, some will be real. So don't forget to just factor sometimes. problems. Like, you don't always have to use the calculator, rely on the calculator. Some problems are factorable. However, if I look at the next big problem, yeah, this one's big. X to the 5th plus x cubed plus 2x squared minus 12x plus 8. So when you have a problem like that, it's very large, expanded, lots of powers up here. Good chance that it's not factorable. So in order to work through this problem, we're going to follow those 4 steps, except I want you to do the rational zero test first. And that would be listing the p over q values. That's like the algebraic support to looking up the numbers in the calculator. Remember, p and q's then 1 in front. So if I'm taking my factors of p, Josh, what are the factors of p?
Like plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8.
And if we divide them by the factors of q, it's just divided by 1. So those would be our possible zeros. So in your calculator, plug in that equation. You're looking up the real zeros that are in this list. So it says list all of its zeros. We want to write it as a product of linear factors. So step 2 would be to graph it and get the real zeros. So see what zeros you have in the calculator. And again, they should come from the list. A 0 is an x equals form. Make sure you have x equals. It's not just the number 2. So a 0 has an x equals. It represents the x value. Carrie, do you have a 0?
-2.
Negative 2? Do you have another one?
Yeah. 1.
1.
Double root.
Awesome. He said 1, and that 1 is special because it's a double root. And you do want to note that, because we're going to have to use that in our problem, the fact that it's a double root. Are there any others in the calculator? No. So we have to be able to find the others. If there are 3 that you can see in the calculator, and my power is 5, that means the other 2 are going to be imaginary. So if I found 3 from the calculator, because you can only see the real ones in the calculator, the remaining ones are going to be imaginary. So looking at the top, those little bullets, the third step says to use synthetic division. So we're now going to use synthetic division. We'll start with the first one. Carrie gave us a -2. Just be really careful. Like, it's already a big problem, but what is it missing? X to the 4th, yeah. So make sure you've got the 0 in place of the x to the 4th. And we're going to do the synthetic division 3 times. So I tried to leave some space there, but if you write really large, you might have to start writing a little smaller. This is why I said the homework, you're going to use synthetic division, which is an easy process, but because the powers are going to be so large, you're going to have to use that process a couple times. And then get a remainder of 0. So what do you do next? We use the -2. We did synthetic division. What do we do next? Brendan?
Do it again with 1.
Yeah, do it again with the 1. So I'm going to keep it like this. I'm just going to place my 0 of 1. Instead of rewriting the answers, I'm just going to keep dividing. Because I'm using those new coefficients, and we're going to divide a second time. Now, if you don't have enough vertical space, I guess you might have to rewrite your answers. So again, divide another time. And you should get a remainder of 0. So I had x to the 5th, I divided once, I had x to the 4th. I divided twice, I now have x cubed. What do you have to do again? Brenton?
Do it again.
Yeah, it's a double root. So because 1 is a double root, we're going to take that 1 And one more time, we're going to do synthetic division. So the fact that it's a double root is pretty important because we need to use it twice. So you'll be really good at synthetic division. So what's the equation that you have left? The 104. Brenton, what does that 104 mean?
X squared plus 4.
Can you solve for x squared plus 4?
Yes.
Yeah. Take the 4 to the other side. Take the square root. Brenton, what is the square root of negative 4? It is a 2i. Plus or minus. So really this is I and the square root of 4. So the negative goes out and makes it the I. And then we have the plus or minus. So the problem said to list all of its zeros. So I have x equals negative 2, x equals 1. And then I can put the 2i and the negative 2i. So here would be my zeros. That's actually the second part of the problem. And then it says to write it as a product of linear factors. That just means your zeros should turn into factors, which are parentheses. So if these would be my zeros, my factors would be x plus 2, x minus 1, double roots, so that means it's squared. That's what the double root implies as a factor. And then I have a 2i, so just plugging that in with an x gives me x minus 2i. And then my negative 2i as a factor would be x plus 2i. So linear factors means each power inside of the parentheses is just an x. So if I look inside those parentheses, it should have mx plus b. Questions? So by now, synthetic division should hopefully be easy, but it's a long process because we had to do it 3 times. So that's why it might take up a little of the space as you're working. So if you look at the one underneath, it talks about complex zeros, which we talked about on Tuesday, and the fact that they are conjugates. They will always occur in doubles, in pairs. So if I have a plus, I have a minus, because we're solving for x squared. And because we're solving for x squared and taking the square root, I always have them together. So you will always have a plus and a minus of an imaginary number, every single time. So this next one is a little nicer because it's x to the 4th. Pretty much wants us to do the same thing. Linear factors list all the zeros. So we actually get the zeros first, and then you use the zeros to write them as factors. So rational zero test, make sure you got that p over q. I know it's annoying, but that's like the, hey, I can use my calculator because I'm getting numbers that are from this list. And we're dealing with 9. So my numbers should be from my p over q list. So find your zeros, and then use division. Garrett, what zeros did you get?
-3 as a double root.
Just -3?
That's all it's on the calculator.
That's all that's on the calculator, so it means the other two are imaginary. So it's important, again, recognizing that it's a double root. And this time, all of those powers are there. So use your -3 and divide. And then Garrett said -3 was a double root, which is an important fact because that means I need to use it twice. So taking the -3 a second time. Colin, do you have these?
Not all the way.
Not all the way. So we bring down the 1.
Then I have 0.
Good.
And then Wait.
So
no,
1,
no, it would be 1.
right,
That's one.
there you go. And then -3, and then that's a 0. So we started with x to the 4th, divided to get x cubed, divided to now have x squared, and it's just a 1x squared plus 1. So again, you're taking whatever you have left. What's that missing part? And solving. So Hannah, what is the square root of -1?
1. So I did plus or minus 1.
Plus or minus 1i. So the zeros that Garrett gave us was a -3 and a double root. And then we have a 1i and a -1i. And again, if you don't want to write the 1 in front and you just want to say I and -i, that's okay. So the last part, just make sure you're writing it in factored form. So having a -3 as a 0 means we have +3 as a factor, and it's squared because it's a double root. So your double root should coincide with your factored form. And then the -i and the +i. Questions? So is it really different from what we did for the first half of the chapter? Not really, no. We're just getting all the answers. Process is so the same. All right, so there's one other type of problem on the top of the next page. Of course, that wants us to use imaginary zeros to find real zeros. And we're not just going to look it up in the calculator, because what fun would that be? Right? I mean, not fun at all.
Cheap and easy.
Yeah, cheap. Yeah, no, yeah, cheap. Yeah, definitely cheap. So it says find all the zeros given that 5 plus 2i is a 0. And then we have x cubed minus 7x squared minus x plus 87. Write it as a product of linear factors and list all the zeros. So that's like standard how all the questions are going to be formed. However, our goal is to use the fact that we know that a0 is 5 plus 2i. And again, we're not looking this up in the calculator because we're going to try and use what is given to see if we can find other information. So if I know that this is a 0, that means x is equal to 5 plus 2i. How many zeros should we have? So looking at the power, how many should we have in our answer? Okay? 3. So I should have 3. Without doing any work, without looking up anything in your calculator, you know a second 0.
The 5 minus 2.
Because?
Because if you have 1, then you have to have the conjugate.
Yeah, if you have 1, you have to have the conjugate. Because the way I get imaginary zeros is by having an x squared and a negative number underneath, because we had to take the square root of it. So we are going to use these zeros to see if we can find the real one, but without looking in the calculator and instead doing algebra. And that's why we're here. We're here to do pre-calc, we're here to do algebra. So we are going to take these zeros and we're going to create factors. So we're going to make them as factors to try and find out what these zeros would have come from. What was their equation? The first thing we're going to do is we're going to move the 5 over. So this becomes x minus 5. And that's equal to 2i. This is also x minus 5. That's equal to negative 2i. I'm going to continue to move things over, so you could have done this in the same step. But the x minus 5, I'm going to put parentheses around that because that's our real piece. Those two numbers are real. X has to be real, the negative 5 is real. And then moving the 2i over, I would have a negative 2i. And moving this 2i over, that's a 5. I'd have a plus 2i. We are going to multiply these guys together. I'm using brackets just to, because I already have parentheses in there and I don't want the parentheses getting mixed up with everything else. So we're going to try and come up with the equation where these zeros would have come from. So essentially, I'm trying to find this equation here because that's what I use to get the imaginary numbers. So where did these zeros come from? What's their equation? We are going to FOIL this, but they are conjugates. And with conjugates, I know my middle terms always cancel. So we're going to FOIL the first terms together. These guys are real numbers. That's my first term.
Keep the x minus 5 like together.
You can keep it together, and if I multiply x minus 5 times x minus 5, that means it's x minus 5 squared. So yes, we're keeping them together because those are the real numbers. And then, Colin, if I multiply the imaginary numbers together, negative 2i and positive 2i make
Negative 4i squared.
negative 4i squared. My middle terms, because they're conjugates, are going to cancel. So that's why I'm only worried about the first terms, which are real, the last terms, which are imaginary. And now we need to multiply this out. So Colin, what is x minus 5 squared? What's that become if I multiply that out?
You get x squared minus 10x plus 12.
Good. And then what happens when you have minus 4i squared?
It becomes negative 1, so you multiply by negative 44.
Excellent. So he said this guy here is a negative 1, so that turns into a plus 4. So my equation is x squared minus 10x plus 29. That's the equation where my zeros would have come from. But we still didn't answer the question, because the question says find all the zeros. And we've just done a lot of work multiplying these zeros together. But it says find all of the zeros and write it as a list of factors. And we're really close. But I'm still missing 1 0. How do you think I could find that remaining 0? Thinking back to what we did at the first half of the chapter, we have to use this to find the remaining 0. We've got to pull this out of the equation we started with. So how would I use this to get the remaining 0? Ooh, Colin, what'd you say? We're going to use long division. So in order to find the real 0 algebraically, we're taking what those two zeros were, we FOILed them together to get this new quantity. To get the one that's real, the remaining piece, we have to divide it out, because that's the only way we can really find that algebraically without using a calculator. We have to divide, we have to factor, we have to break something down. So we're dividing with that x cubed minus 7x squared minus x plus 87. So this is a great problem because it involves remembering that a complex 0 occurs together in a pair, but it also involves some FOILing and then some dividing with wonderful synthetic or long division. So remember, the other two terms you ignore. We have an x, we want to make it x cubed. And then I multiply everything by that value of x. Don't forget that you're subtracting everything. So I end up with a 3x squared minus 30x and then plus 87. So if I have an x squared and I have a 3x squared, I need to multiply it by a 3. And hopefully 29 times 3 is 87. Because you should get a remainder of 0. If you don't, then you did something wrong. So my final 0 that we could have cheated and looked up in the calculator, Dylan would have rather done that. Oh, well then you're good to go. You don't need to cheat.
Yeah.
My final 0 is x plus 3. So that means my final 0 is negative 3.
Bam.
Questions? That's like a fantastic problem. I'll pull my answer down again.
That's just
Nice and
Fantastic problem.
Is that all
Yeah.
the homework?
Yeah. So tomorrow we're going to wrap this section up, and there'll be time for you to work in class on the homework for the weekend. So tomorrow is a wrap up. You might have to pull out the quadratic formula for one of those problems.
Oh my gosh. It's a dream come true.